can come true if we have the courage to pursue them. It's an immense pleasure in welcoming you all for the inaugural function of the International Seminar on Topology through virtual mode, organized by the Department of Mathematics, Konganadu Arts and Science College, Coimbatore. Change can be accomplished, most of all, the power of prayer, because with God all things are possible. Let us feel the presence of Almighty through the invocation by Miss Shamli Segin, MSc Mathematics.
അറിവിലെ തെളിവ് നെഞ്ചിലെ ഉറുതി അകത്തിലെ അൻപിനോർ വെള്ളം പുരകളിൻ മീത് തനിയരസാണൈ പൊഴുതിലാം നിനത് പേരരുളിൻ നെരിയിലെ നാട്ടം കർമ്മയോഗത്തിൽ നിലയ്ത്തിടലിരുളായി കുറി ഗുണമേതും ഇളതായി അണൈത്തായി കുലവിട തനി പരം പൊരുളേ പാരം പൊരുളേ പാരം പൊരുളേ.
Thank you, Shamli, for letting the goodness sparks to a spiritual change reactions with your angelic voice. We must welcome the future, remembering that soon it will be the past. And we must respect the past, remembering that it was once all that was humbly possible. Now I request Dr. V. Gokulamani, head of our department, convener of this international seminar, to spray the sweet aroma of happiness through the words of welcome.
A graceful and pleasant evening to one and all present here. I feel it very much humbled and privileged to welcome you all to the International Virtual Seminar on Topology and its applications, organized by the Department of Mathematics, Konganadu Arts and Science College, Coimbatore. It's my great privilege to welcome the chief patron of this prestigious institution, renowned academician, source of inspiration and great support, our dynamic secretary and director of our college, Dr. C.A. Vasuki Madam, to this seminar. I welcome you, ma'am. I welcome our most respected principal, Dr. M. Lakshmanaswamy sir, whose encouraging words stood firmly behind the success of all our activities. I welcome you, sir. On behalf of the Department of Mathematics and entire fraternity of our college, I accord my heartfelt welcome to the resource persons of the event, Professor S. Syed Jafari sir, Mathematical and Physical Science Foundation, Denmark, Dr. Hakim A. Othman, Associate Professor, University College of Al Quds, Saudi Arabia, Dr. S.S. Benjali sir, Professor retired, Department of Mathematics, Karnataka University, and Dr. M. Parimala, Assistant Professor, Department of Mathematics, Bannari Amman Institute of Technology, Erode. Respected professors, we look forward for your innovative knowledge sharing sessions that will open up new vistas of wisdom that will radiate the source of energy within us. On behalf of our department and on my own behalf, I take immense pleasure in welcoming you all, sir. I take this opportunity to welcome Dr. S. Palsamy sir, Dean Research and Development, for rendering his constant support and encouragement in all prospects of this program. I welcome you, sir. I am very much delightful in welcoming Dr. S.R. Madan Sankar sir, Dean Academic, for his gracious presence and for all his enthusiastic support. I welcome you, sir. I take this opportunity to welcome our most respected Chief Executive Officer, Dr. V. Sinnusamy sir, Dr. M. Murugesan sir, Controller of Examination, Dr. V. Sujata Madam, IQAC Coordinator, and Dr. R. Sendil Kumar sir, Librarian, to this seminar. A warm welcome to you all. I feel blessed to welcome former principal and head of the Department of Mathematics, retired, of our college, Dr. R. Devi Madam, my teacher. I welcome you, ma'am. It's my great pleasure to extend a cordial welcome to all the heads of various departments, faculty members, research scholars, and students from our own institution and other institutions to this occasion. Welcome you all. I also extend my hearty welcome to my dear colleagues who rendered their wholehearted sustenance to make this program into reality. I welcome you all. Dear participants, I assure that this program will provide you all with an essential ingredients for exchange of knowledge. So think new possibilities and make use of this platform to achieve your destination. Once again, I welcome you all. Thank you.
Thank you, madam, to unfold our department horizons and rejoice in the simple pleasure that has been bestowed with.
There is something so special about the great women who focus with purity, works with integrity, leads with quality, and shine with beauty of heart. A potential leader and a great motivator who paves the way for us and enjoys our success is our most respected Secretary and Director, Dr. C.A. Vasagi Madam. Ma'am, I humbly request you to deliver the presidential address. Ma'am, please.
Thank you. Thank you. And good afternoon to all the participants who have gathered here. I'm really proud of our mathematics department. First and foremost, you're all alumni of this institution and you're all great researchers. You don't just stop great teachers and researchers. So I'm very proud of this department who had organized today this international virtual seminar on topology and its applications. And you have called excellent guests because always exchange of knowledge from various parts of the world is important. Otherwise, we'll become a frog in the well. And today you have invited people from far and wide, Dr. Saeed Jafari from Denmark, and Dr. Hakim Othman from Saudi Arabia, and Dr. S. Bechali from Karnataka. And I just recollect, Mr. Benchali, you have visited our institution, and I'm very happy that you have joined today this seminar. And also our Dr. M. Parimala, who is from Banari Institute of Technology, Satyamangalam. You're all, and also a lot of active participants, our students, research scholars, our teachers, our deans. I'm glad that all of you have joined very enthusiastically. Let me tell, whenever the mathematics department, they invite me, I always have an apprehensive to join y'all, because I am truly a biologist. My major being zoology. I always thought I'm very far away from y'all. But only I should thank each and every one of you for inviting me, because this made me think and read, oh, what is the relationship between topology and biology? And to the amazing surprise, I came to know that it has a lot of relationships. So thank you, dear friends. And I would like to quote few things like how we are very closely linked as biologists with you all. There's a very famous saying, how you differentiate between how the mathematicians think and how the physicists think. And let me tell you, the difference between mathematicians and physicists is that after physicists prove a big result, they think it is fantastic. We see all these people, rocket people, don't we think? Even before the rocket takes off and lands, they think they have achieved great. So that's the mentality of the physicist. But the mathematicians, even though after they prove a big result, they think it is very trivial. Isn't that wonderful? So that's how mathematicians think. So there is a great difference in how you think. That's what makes the budding mathematicians and already established mathematicians into great scientists and thinkers. And let me tell you how this topology, which is a branch of mathematics, has it has which generally first and foremost I came to know because I'll ask all my staff members, what is it? What is topology? And they said it is the geometric properties and spatial relationships. This is what is topology. But when I really read and how it is applied in biology, it really surprised me. A branch of topology that is called, you call it as knot theory, and it is used in biological studies to determine the effects of certain enzymes, to study the structure of DNA and topoisomerase and gyrase. It's used in genetic research. So that's very interesting because ultimately everything falls into, when you see all the the how we perceive, how you look at things, you make an opinion about how it looks and what is the structure of it, isn't it? This is the common how the human mind acts, and that very interestingly mathematicians have calculated and given a branch called topology. That's how I think. And the other thing, when you see in evolutionary biology, many current research topics, when you look about genetics, especially the phylogenetics, how based upon the um, genetic makeup, you actually separate them into different phylums and classes and subspecies and species. So how this topology is used in various biological entities, especially in species and up to even genetic, the individual gene level. So that's something which really very interesting factor, how mathematics is very closely linked to us. And another important branch, which is really upcoming at the moment, and some of our now the recent Nobel Prize, which was got for CRISPR technology, the gene, how you slice the gene, that is called CRISPR technology. In that, topology is used. Isn't that amazing, dear mathematicians? Because there are so many research scholars who have joined, and this is something, a thought for you all to actually research into and make some certain hypothesis and think about solving, because generally all research, and they really, when you see how this CRISPR technology is used, is it is called DNA origami. Origami is how you cut the papers and how there's a different designs what you make in paper designs. It's very famous, it's connected with Japanese. And this DNA origami, in topology, they have calculated how this drug delivery system acts and how this DNA molecule acts as a carrier, and it takes this drug and delivers to the specific points. So this is what how it is used in very fine genetical research. So that's very interesting. And also, when you see in physics, it is used in cosmology, in quantum field theory, and in overall, when you see how in cosmology it tells you the shape of the universe, and also lot the space time research, and even a lot of unsolved mysteries like black hole theory, which in our Bharat, we have already, our Ramanuja, people like Ramanuja have already come up with this. Now it is something, it is a very hot topic in the world of science, physics, and maths. So that's how the mathematical, when you see our country, Bharata, yeah, our India, the India is like Bharat, nothing but Bharat, our Bharat Varsha is a land of mathematics, to be true. And the legendary Ramanuja, nobody can forget about him, even though he was not a person who learned maths in a very systematic way. The whole world of maths today cherishes our Ramanuja. During his very short lifestyle, he had a lifespan. He hardly lived for 35 years. Nearly 3,900 identities and equations has been given by him. And I was just talking to one of the maths professor. He was telling um, uh, some of these Ramanuja's theorems and his problems and solutions, what he has given, is now used in our ATM machine. Isn't that something? See, this is what mathematicians always think about something, give a solution and give a theory and how you solve it. But the biologists, the physicists, we apply to day-to-day use. So this is how it all works. And when you can talk about Ramanuja so much, because Coimbatore is not very far from where Ramanuja got his inspiration. It was the birthplace of Ramanuja is not very far away from us. It is hardly 100 miles, and that's where Ramanuja was born. And when you see, he was very, Ramanuja credited his mathematical capacities to divinity. He didn't say it was all his achievement. He always said, how was this, how did you solve this problem? And he used to come up with, no, this today, after praying to our Namagiri Tayar, that is the deity in Namakal, he used to come up with this solution to a particular problem or theorem. It really amazed the Western thinkers, especially in Cambridge. Today, he's most celebrated person, and he got so many awards. And all these awards and accolades, he always dedicated it to the our Almighty God. So an equation for him, he said, in his own words, I would like to tell, an equation for me has no meaning unless it expresses the thought of God. Isn't that's a great thought? Because we always, as people from Bharata, we relate everything, anything to God. Whatever that lives on this earth, whatever is created, is all dedicated. It is all the all we dedicate to the Almighty. So that's one. And also in India, when you see the architects, because this topology is a lot to do with shapes and geometric shapes, I always used to think, whenever I go visits all these great temples, how on earth have these huge monuments, like, huge buildings, like, they are made out of solid granite. First of all, how are they standing? And people say it is, there is no cement like or binding anything to bind it. It is only interlocking method. There must be some mathematical calculations involved. You cannot just go and just construct a temple. They are still living today, like, today you can, when you visit South India, you can see these great structures. And there are some, most of these temples, great temples, like from Madurai to Tanjore to Rameshwaram, there are 1,000 pillar structures will be there. You call Ayiram Kal Mandavam. You people just go and see how on earth the alignment they have done is so precise. It's unbelievably precise. And how has that been done? And how these structures, temple structures, have architectural beauties and wonders, I would say. I would always say, I don't debate like the 7 wonders of the world are not as good, but probably people didn't visit South India, and probably they haven't seen these wonders, which have been made 2000 years back. And these, when you see some of these structures, what they have done are so astronomically connected. You see the sun rays, they will say, will fall on this particular pillar on this particular time, and it will. And you will be really surprised when the moon comes to the, that is on the full moon day, the rays will fall on this particular pillar, it will. And this has been happening for thousands of years. So these are all something, unless you have the mathematical knowledge and calculations and your whatever, today you would have given a new name, and like topology or whatever it may be. The knowledge of this already existed thousands of years back in this great country. So today I would like to thank my dear friends for this conference that you have organized, which is a great knowledge sharing between various countries. And also it's very important as I said, sharing knowledge to make our research should be interdepartmental and it should see, mathematics should not only always align with chemistry or physics, it should always align with biology and so many other branches. So that's how today when you go to research on the higher level, it's all very interconnected. It's very, very nice to know that. And to conclude, I know it is going to be a big session today. You have great talk speakers from all over the world. I would like to conclude by saying this quote: maths is a security, certainty, truth, beauty, insight, structure, and architecture. So I see mathematics as the part of human knowledge that I call mathematics as one and only one great glorious thing, whether it is differential topology or functional analysis or your graph theory and so on and so forth. You have so many branches, but all these are ultimately intimately interconnected, and all these facets are nothing they have so much close relationship. And all your research, dear friends, it should help the humanity to live more happily, more peacefully, and as I always say, as Vasudeva Kudumbakam, where Loka Samasta Sugino Bhavantu, that is, let the entire world be together, where love and happiness should always persist in all your minds. Research should take you to that level. And that's what I feel mathematics is to me. And I wish this program a grand success and good luck to all of you. Thank you.
Ma'am, thank you so much for appreciation our department. You may be far away from us with the subject, but you are always with us in all our endeavors. Thank you, ma'am, for an idol of knowledge, experience, and inspiration to all of us. A word of appreciation will make ordinary things extraordinary. We are delighted to have our beloved principal, Dr. M. Lakshman Swami, sir, to enlighten the mathematics community with this message. Sir, please.
Thank you, Mohanapriya Madam. Good afternoon, one and all present here. Most respected Secretary and Syndicate Member of Bharatiya University, Dr. C.A. Vasili Madam, and our former Principal, Dr. Devi Madam. Today's our program resource persons, Professor Dr. Syed Safari from Denmark, and Dr. M. Parimala from Satyamangalam Erode. Convener Dr. V. Kovilavani, Head Department of Mathematics. Coordinator Dr. M. Vigneswaran. Organizing Secretaries Dr. M. Vivek Prabhu, Dr. B. Sadish Mohan, faculty members, research scholars, and my dear participants. On behalf of the management, once again welcome you all for the international virtual seminar on topology and its applications. Topology is the study of geometrical properties and spatial relations unaffected by the continuous change of shape or size of figures. The way in which constant parts are interrelated or arranged, topology of a computer network. And topological group is a group G together with a topology on G such that both the group's binary operation and the function mapping group elements to their respective inverses or continuous functions with respect to the topology. A topological group is a mathematical object with both an algebraic structure and a topological structure. Thus, one may perform algebraic operations because of the group structure, and one may talk about continuous functions because of the topology. Topological groups along with continuous group actions are used to study continuous symmetries, which have many applications. For example, in physics, in function analysis, every topological vector space is an additive topological group with the additional property that scalar multiplication is continuous. Consequently, many results from the theory of topological groups can be applied to function analysis. With these few words, I congratulate the Maths department for your excellent effort. I am also eagerly waiting for the chief guest speech. Thank you for the opportunity. I wish the program a grand success. Thank you.
Thank you, sir, for your enriching and thought-provoking message. The admiration of genius makes one aspire for excellence in life that creates the harvest so abundant. Let's have a glimpse of introduction about today's chief guest by Dr. D. Vijayalakshmi, Assistant Professor of Mathematics.
Vidya, am I audible, Vidya?
Yes, ma'am, it's audible.
It's a great honor for me to introduce a very great researcher in mathematics, Professor Dr. Said Zafari sir. Professor Dr. Said Zafari sir received his Master of Science in Mathematics and Philosophy in the year 1993 from Aalborg University and Copenhagen University in Denmark. He studied relativity theory, statistical physics, and quantum physics at Aalborg University in 1994. He received teaching position in mathematics and philosophy at the College of Vestjylland South in Slagelse, Denmark in the year 1994. In 2004, he received Dr. Rerum Naturalium from Technis University Grace under supervision of Professor Dr. M. Ganster. Professor Jafari has been doing research since 1993 in the areas like topology, fuzzy and digital topology, functional analysis, mathematical physics. He has more than 25 years of teaching and research experience. He published more than 400 research papers and he is a member of the editorial board of several mathematical journals. He has done review works for more than 20 journals and also for Central BAT and mathematical reviews. He has been external examiners of more than 40 PhD students, mostly from India. At this juncture, on behalf of our Department of Mathematics, we thank Zafari sir. He has been invited speaker to several international conferences and workshops in mathematics. He is the founder of the newly ongoing research center, Mathematical and Physical Science Foundation in Slagelse, Denmark. I'm profusely overjoyed to take the opportunity to introduce our chief guest of the day. Now, I kindly request our chief guest, Professor Jafari sir, to deliver the inaugural address. Sir, please.
Thank you very much for the presentation. I thank you very much, the organizing committee, which made this seminar possible. So I am really honored to be here to give this inaugural talk and then followed with my special talk about topological groups. So I can see one of my colleagues earlier talked about topology and its applications. And there are not so much to tell because as she said, and the principal also told about that the topology concerns shapes and patterns. Actually, mathematics concerns math patterns, and regularities. So I will show what I have about this. I hope you can see it. What is topology? Actually, the subject matter of topology is to study some invariant properties. Why invariant properties of spaces? Because we humans do like invariant and regular things, to see that this happens again and again. This, of course, under the condition which we have a continuous deformation. And you have certainly heard about, for example, rubber sheet geometry. And again, why rubber sheet? Because objects under consideration behave like rubber. For example, if you have a, if you studied, for example, the book of topology, from Borisovich and Fomenko, you can see that if you have a triangle, then you can deform it to a circle, and the circle can be deformed to this infinity figure, which also can be used in knot theory that our colleague talked about, utilizing it in the biology. You can see in DNA, for example, and so on. So if we go back and see the book of History of Topology by James, it says that the rise of theory of sets, and particularly the theory of sets of points, what in German called Punktmannigkeit-Lehre, it means that the teaching of the manifold, because manifold consists of points, was due primarily to creative work of George Cantor. His point set theory added entirely new perspective to topological thinking, and Cantor published his most important investigation into the theory of sets of points in a series of 6 papers entitled Über endliche linear Punktmannigfaltigkeiten. It means that on infinite linear manifolds, which is published in the famous Journal of Mathematische Annalen during these years from 1879 to 1883. And these brilliant papers constitute the quintessence of Cantor's life work, as Ernest Husserl, another mathematician well known, has declared. So, but what is this notion which Cantor come along with? And the most important notion which Cantor studies in the notion is the notion of limit point. And he came to this notion when he studied point sets in Euclidean n space. This notion can be seen in the Bolzano and Weierstrass theorem, which says that every infinite set of points in a bounded region of n space possesses at least one limit point, which everybody knows concerning this. You know, it is from analysis, and also it is intermingling with topology. And the notion of limit point was the Cantor's motivation to come to notions such as drive set, and everywhere dense set, an isolated point set, nowhere dense set, and Cantor's middle set is continuum. So then comes Giuseppe Piano and Camilla Jordan utilize this the Cantorian ideas in geometry, and their research work played an important role in the development of point set topology. After that, then came Poincaré with Topositus, and Fresha and Ridge, and many others, of course, Hoff, Hausdorff, Hilbert, Sierpinski, Alexandrov, and Bourbaki. Therefore, one can conclude that the set of real numbers are the most important notions in mathematics. Actually, it was the set of real numbers which was, it means the real numbers was raised to metric spaces, and metric spaces to topological spaces. For example, if you take a function from real number to real number, then you can define continuity, which everybody knows in this seminar, at the point A with sigma and epsilon notation. And afterwards, you can define metric spaces, and then you can make the conceptual jump and free ourselves from the independence of the distance function, and yet retain the properties of continuous function that we have seen so far in research areas. So topological space is defined as a set X with a collection G of subsets called open sets satisfying these 3 conditions. X and theta are open sets. Any union of open set is open. An intersection of finitely many open set is open. So there are many people, mathematicians also nowadays, that have conflict with this definition. They think that this definition actually is raising some contradictions in mathematics, actually, for example, in physics and so on, because our colleague talked about the usage of topology in other part of science, for example, in physics and so on. That's why the open sets, because the real numbers are not defined properly and so on, But I think we can use it, and in 3 dimension we have no problem with that. So we already have the applications, and we can see, for example, well, GPS and cars and so on. So the application of it is very fine. So there is no problem there. A metric space is a special kind of topological space. The important notion besides open sets are, of course, closed sets, the interior of a set. Because if we don't define interior of a set via real numbers, then you cannot define open set, and so neighborhood and so on. It means that actually you can define the topological space with closeness or neighborhoodness or nearness, which some from South Africa and also in Germany actually working with category theory, and they studied in that way. So basis is very important, and first axiom of countability, and second axiom because they are using this second axiom of countability in defining, for example, differentiable manifolds. And then comes continuity and homomorphism, relative topology, Cauchy sequences, and compact sets, and so on. So after that, one can ask very usual question, typical question can be that how many holes are there in an object? For example, here you can use cohomology theory. Actually, Theorem cohomology theory or homology theory are studying these holes. That's why, for example, in particle physics, in mathematical physics, in string theory, we have Calabi-Yau manifolds, which there are 3 holes, and these 3 holes represent actually the 3 generations of particles in physics. And how can you define the holes in a torus or sphere, or what is the boundary of an object, and why we have different geometries, for example, Lobachevskian geometry, and we have Riemannian geometry, and so on. Is a space connected, or maybe it is simply connected, and so on? Does every continuous function from a space to itself have a fixed point? So there are usual questions. One can also have other questions. But here, topology is relatively new branch of mathematics. And it started actually in 1900 when it is formulated properly. And the following are some of the subfields of topology, which we talked about, for example, general topology and Poincare topology, which normally considers local properties of spaces. And we are interested in local properties. And of course, we want to see that this can be generalized to global, but it is very difficult because we don't know what a space is physically, you know. So it's closely related to analysis, of course. And it generalizes the concept of continuity to define topological spaces in which limits of sequences can be considered. Sometimes distances can be defined in these spaces, in which case they are called metric spaces. Sometimes no concept of distance makes sense. So we have combinatorial geometry as a topology. Then, everybody knows Euler from Switzerland with so many results, like Ramanujan. And the combinatorial topology considers global properties of the spaces. And one of these, which everybody knows working in graph theory, that V minus E plus F has a constant, actually, number, because V and E are numbers of vertices, edges, and faces of an object. For example, a tetrahedron and a cube are topologically equivalent to a sphere, and any triangulation of a sphere will have an Euler characteristic of tau. Then we have algebraic topology, which also considers the global properties of spaces and uses algebraic objects such as groups and rings to answer topological questions. Algebraic topology converts a topological problem into an algebraic problem that's hopefully easier to solve. For example, a group called a homological group can be associated to each space, and the torus and the Klein bottle can be distinguished from each other because they have different homologic groups, and you can see it here. So algebraic topology sometimes uses the combinatorial structure of a space to calculate the various groups associated to that space. Then we have differential topology, which considers spaces with some kind of smoothness associated to each point, because if you don't have smoothness, then you cannot define tangent lines and so on. Of course, if you use bundles and so on, then we have another case, yes? In this case, the square and the circle will not be smoothly or differentiable, equivalent to each other. Differential topology is useful for studying properties of vector fields, such as magnetic and electric field. Topology is used in many branches of mathematics, as our colleague earlier also mentioned that, such as differential equation, dynamical system. When we talk about dynamical system, also, when we study, for example, with differential equation or micro-local differential equation or partial differential equation, for example, biology or other cases, then you can see that actually the problem is very complex. So in this case, it is useful to use topology, and also in knot theory, which we know also it can be used also in other branches of science, and Riemannian surfaces in complex analysis. For example, the recent works of Professor Mariam Mirzakhani, who died actually recently and got the Field Medal, studying this and solving actually many problems in this relation. It is also used in string theory in physics, and for describing the space-time structure of universe. Actually, the string theory is not falsifiable. It means that if you have a distance of 10 power of minus 33, then it is no hope actually to do experiment. Actually, one of the founder of this area, Professor Nielsen from Copenhagen University, he doesn't work anymore on this theory, and he says that in this case we cannot actually read off the mind of God. Then so we should work with arbitrary actually dynamics, he calls it, and we cannot go down there, but we can actually study the phenomena which we can see here. So this is the use of topology, and I think I made my point clear concerning this, which the topology actually uses can be used everywhere, and mathematics is the language of nature. So this is what I wanted to say about topology, and those who are interested, they can study the book of James, the history of topology. Or, for example, I have another book, A Geometric Introduction to Topology by C.T.C. Wall. It is also very interesting to study it. So I go to another my talk. Which I use it. I will, yes.
Thank you, sir, for your wonderful address and for giving an introduction about topology and its application in various fields. Looking forward for your lecture in the technical session, sir.
Yes.
Enjoy the little things. For one day, you may look back and realize they were the big things. Acknowledging the good that you already have in your life is the foundation for all abundance. I request Dr. M. Vigneshwaran, coordinator of this international seminar, to acknowledge the good hearts. So,
good evening to all. It's my privilege and pleasure to propose the vote of thanks on behalf of the organizers. First, I thank a man with high vision, a man with knowledge, a man with unbelievable willpower, a man with commitment, who is none other than our President, Dr. M. Origami, sir, who raised this institution to the highest position. He also motivated us to do quality research always. Thank you, sir. Next, I thank a woman with high potential, a woman with courage, who is our beloved Secretary and Director, Dr. C.A. Vasihi Madam, who is our guiding force behind raising this institution to the College of Excellence status awarded by UGC. Thank you, Madam. I thank our Principal, Dr. M. Lachimasamy, sir, Chief Executive Officer Dr. V. Sinusamy sir, Dean R&D Dr. S. Balasamy sir, and Dean Academics Dr. S.R. Madan Sankar sir for their constant motivation and encouragement. I render my sincere thanks to Dr. R. Devi Madam, former principal of our college and former head of the Department of Mathematics, and my guide for her continuous motivation and guidance. My sincere thanks goes to Professor Dr. Syed Jafari, Mathematical and Physical Science Foundation from Denmark, and Professor Dr. Hakim Athman from Saudi Arabia, Professor Dr. S.S. Benchali from Karnataka, and Dr. M. Parimala from Bannariyamman Institute of Technology, Tamil Nadu, for accepted our invitation to deliver the invited talk in the International Virtual Seminar on Topology and its applications. Thank you to all. I also thank our HOD Madam and my colleagues for extending their hands in organizing this international seminar. I thank all the participants for their presence in this international virtual seminar on topology and its application. Thank you, one and all present here.
Thank you, sir. Now it's time for the technical session. We take immense pleasure to recognize the valued presence of our valiant guest of the day, Professor Dr. Syed Jafari, sir. We humbly request you to take over the session. Sir, please.
Thank you very much. Today I will talk about, let me see, I have it here. I want to talk about topological groups. I want to find, I don't know why it doesn't come. Then there, just a minute, I just want to find my file so I can present it. Yes, I found it. Thank you very much. Well, about ideal topological groups, which I made this paper with Dr. Rayesh for a year ago. I think that I thought maybe it is useful actually to introduce ideal and topological groups, which my aim was actually to find examples which otherwise were difficult to construct, or what concern topological groups. The concept of ideals in topological spaces has been introduced and studied by Kuratowski, Ainvadiana, Kaswami, which you can see the books, topology, and also the localization theory, inset theory. There you can find actually the introduction of the notions. An ideal I on a topological space is a non-empty collection of subset of X which satisfies two conditions. A belongs to the ideal, and B is a subset of A. So if these two are satisfied, it means if A is belonging to the ideal and B is a subset of A, then B also belongs to I. Second, if A belongs to I and B belongs to I, implies that their union also belongs to I. Then we have, if we have given a topological space, X and tau, with an ideal I on X, and if Px is the set of all subset of X, a set operator is defined by this point star Px to Px, called the local function of A with respect to tau and I, is defined as follows. For every, taking for example a set belonging to X, A star can be defined as X belonging to X, which the intersection of U with A is not in I for every U belonging tau of X. And tau of X actually is that the place which will have all these U belonging to X and X belonging to U. So if you take, for example, a neighborhood, for example, of X, a point. If I is an ideal on X, then X, tau, and I is called an ideal topological space. Actually, we have made lots of papers with Professor Parimala about these notions. Here we study the class of ideal topological groups by using I open sets and I continuity. And if we take this, or simply we call G star and tau and I, simply called G, will denote a group endowed with a topology and ideal, which is this ideal is something new, which we introduced. Actually, topological groups, there are three conditions which define topological groups. If I get to write something here. So we have a group, okay, and we have a topological space, okay, and we have the map which we take, for example, G, let's call this 3, multiply G, and take, for example, X and Y. This will be sent to X and the inverse of Y, and both of them, the multiplication is belonging to G, which is continuous. You can see that everything is connected, yes? Of course, one can define the third axioms conditions in some other way. You can say, for example, okay, we can do it such as that G multiply G. I write it here up because I have no place for it. G multiply G. We have X and Y. It's sent to XY belonging to G, which is continuous, okay? And then we have if you take, for example, G, which is X belonging to G, then X minus 1 also belonging to G, and this is also continuous, okay? This is also is continuous, okay? So we can actually add two conditions, statements, instead of 3, okay? So this is any notion which is either group theoretical, abelian, or topological, connected, compacted, etc., can have a meaning when applied to a topological group. So let's go here. The identity element of G is denoted by E, and the E of G, when it is necessary, the operation which goes from star and G multiply G goes to G. Also, this type of usage can be used also in Lie group theory. So it is interesting. I'm talking to those who are doing research, interested in type of research, whether we can introduce ideals also in Lie groups, which you have also differentiable manifolds. Okay, yeah, and topological groups, of course. If we go from X and Y, and we can see that this operation is defined as X star Y, it's called a multiplication mapping, and sometimes denoted by M, and the inverse mapping I, which goes from G to G, and sending X to inverse of X is denoted by I. And X and Y denote topological spaces on which no separation axioms are a priori assumed. So we take a subset S of an ideal topological space. We call it I open. I think this notion is defined by some Egyptian mathematicians, Abdel Munsef and others, I think so. If, or Nasif, I don't remember, but I know that they have defined this E open if S is the interior of S star. But I think this notion also introduced by Hamilton and some other, Hamlet and others, yes. The complement of an I closed set is said to be an I open set. So definition, a function f which goes from a topological ideal topological space to another ideal topological space is called E continuous if the inverse image of V as a V belonging to sigma is belonging to IOX. It means the ideal open set. E open if FAU is belonging to IOY for every U belonging to IOX, and E closed the same. You can see it. So, if you have FAU is belonging to IC, it is a closure of Y for every U belonging to I closure of X. You have definition 2, a topologized group, which is G star tau I, is called an ideal topological group if for every X and Y belonging to G and each neighborhood W of X star Y in G, there exists I open set neighborhood of U of X and V of Y such that U, the operation, it means U star V is a subset of W. Then we have this result. If we have a ideal topological group, then it is true that if A belongs to if A belonging to IOG, let me see, you can hear me or what? Can you still hear me?
Yes, sir. Yes, sir.
Okay,
It's
no
audible.
problem. Okay, no problem. Thanks. So we have definition 3. A subset A of a group G is symmetric if A is equal to inverse of A. And we have definition 4, a bijective function from one ideal topological space to other one is said to be I homomorphism if it is I continuous and I open, which is similar to the definition of actually homomorphism when introducing ideals. But the example is not so easy to make. So we have the Theorem 1.
Sir, we can't hear.
Sir, it's not audible, sir.
அப்படின்னு என்ன வச்சேன்
Sir, Jafari, sir, it's not audible, sir.
கொடுத்துட்டாங்க அது எங்க கொடுக்கணும் மெசேஜ்
Dear participants, please stay in the line. There is some technical issues there. So we will rectify it and we will let you soon. Sir? Sir, it's not audible, sir. Jafari, sir, it's not audible.
Oh, sorry. This is my computer. Something happened. That's why.
No problem, sir. No problem, sir. Now it's
Okay,
audible, sir.
I will find the file again.
Yes, sir.
Let us see what to do about it. Yes, sorry for that. So I hope you can see it. Again?
No, sir. No, sir. It's now it's presenting, sir. Now it's presenting. Yes, sir. It's visible now.
Okay, that's nice. That's nice. I have been here because I want to show one of the results we got. We have a topological, ideal topological group. Then each left-right translation is an I homomorphism, which we proved it as follows. Well, I give a sketch of it, and those who are interested can get paper from me, or they can get it from ResearchGate. And the statement for the left in translation one can prove, and the other one for the right is analogous. Of course, left translations are bijective mapping and prove directly for every x belonging to the group G. The translation Lx is I continuous. Let Y be an arbitrary element in G and W an open neighborhood of Lx of Y. The left translation, which you are apply on Y, which is actually the operation of this ideal topological group X star Y, which is equal to E star Y minus minus 1. By definition of ideal topological groups, there are I open sets U and V containing X and Y minus 1 respectively, such that U star V minus 1 is a subset of W. In particular, we have X star V minus 1 is a subset of W. By a lemma which I taught earlier, lemma 1. Because of this lemma, then we have the inverse of V is an I open neighborhood of Y, so that the last inclusion actually says that Lx is I continuous. It means that the left invariant is I continuous at Y. So the rest is the same, and easily one can follow it. So there is no problem there. One can also show that variant is an I open mapping. We go to the next, which we have Theorem 2. We have a topological ideal topological group, and let beta of E be the base at the identity element E of G. Then we have for every U belonging to this base, there exists V, which is ideal open, such that V2 is a subset of U. Oh my God. I hope I can follow this. I can do my talk, because always comes something. I don't know what it is. For every U belonging to this base, there exists V belonging to ideal open of the G and E, such that V minus 1 is a subset of U. For every U belonging to this base, there exists V belonging to the IO GE, such that V star X is belonging to is a subset of U, or included in U. So probably one, which we have an ideal topological group, and X is an element of G, then for any local base at E, each of the families, if we define it like beta X is equal to E star U, which U is belonging to the base, and X star U minus 1, such that U belonging to the base is an I open neighborhood system at X. Then we have definition 4. An ideal topological space is said to be I homomorphism if for every X and Y there is an I homomorphism F of the space. And this is folklore, because now everybody knows that, but this can be used actually in the following results, which we have. Let me see. Every ideal topological group G is an I homogeneous space. And we know that homogeneous spaces are very important in mathematics, actually in differentiable manifolds, also in Hamiltonian mechanics and symplectic geometry. So if we took the proof of it, take any elements X and Y in G and put Z is equal to x minus 1 star y, then we can see that the left invariance of z is an I homomorphism of G, and the left invariant of z of x is x star z, and x star taking the inverse of x star y, which gives y. And we have the next theorem. Let this that G star tau I be an ideal topological group and H be a subgraph of G, then H contains a non-empty I open set. Then H is an I open set in G. Every open subgroup H of an ideal topological group is also an ideal topological group. So this is called the ideal topological subgroup of G. Term 5. Let's given an ideal topological group, then every open subset of G is I close in G. So definition 5, a function, it is called I irresolute if the inverse image of V is I open in ideal topological space for every J open in ideal topological space Y sigma J. So we have the theorem 6, which concerns topological groups. Let F, which goes from G to H, be a homomorphism of ideal topological groups, not homomorphism, but homomorphism in group theory. If F is I irresolute at the neutral element E of G, then F is I irresolute, and thus I continues on G. So this is a good result, which one can introduce is irresoluteness. Definition 6, an ideal topological space is said to be I regular if for each closed set F, a subset of X, and each X belonging to X minus X complement of F, there are disjoint sets H and W belonging to IOX, such that F is belonging to is a subset of H and X belonging to W. So you can see that one can also talk about the basis of neighborhood of E in topological groups and receive actually other results. But I focus on some of the results simply to present, because some of the results are very complex and the proof also long. Term 7, you have a ideal topological group with a base E at the identity element, such that for every U belonging to the basis, the base, B beta of E, there is a symmetric I open neighborhood of V of E, such that V star V is belonging to U, then G satisfies the axioms of I regularity at E. So this is also well known, but converted to topological groups. But of course, one should also find out that generalized linear group are a good source of examples to find topological groups in this case. Also, this which we proved concerning I regularity, you can see that in a topological groups, we say that it is regular if for every neighborhood U of a set A, we can find the closed neighborhood V of this set A such that V is subset of U. So there are sorts of examples. One can use additive group of real numbers. Actually, this is a good source, which one can also make examples there. So theorem 8, if G star tau I is an ideal topological group, then I closure of A is a subset of A star U holds for every subset A of G and every open neighborhood U of E. This is a proof. You can see it that it is the same as the case with topological group with ideals, but I think one should find examples for it. We didn't find example for this case because since This is an ideal topological group for every open neighborhood U of E. There exists V belonging to IO G of E such that the inverse of V is subset of U. If you take a point of in the closure, ideal closure of A, then we can see that X star V is an I open neighborhood of X. Then there exists a point A belonging to the intersection of A and X star V, and that's A is belonging to X star V. This implies that A is equal to A star B minus 1 inverse of B, which is belonging to A star V inverse of B, and in this case, it is a subset of A star V. That's why this is a subset of I closure of A is a subset of A star U. Because of time, I cut the proofs. It takes lots of time if I want to go through them. So I just mentioned the results, and I let the proofs be in the paper. If you want it, you can just get it from me. So definition 7, an ideal topological space is called IT2 if for every two different points of X there exists disjoint I open sets U and V of X such that X belonging to U and Y belonging to V. So we have this theorem which concerns I regularity in IT2. We have an ideal topological group, then it happens that actually the ideal topological group is irregular on IT2 space. This is a proof. I don't go through it. So we have definition 8. An ideal topological space is said to be I compactive for every cover of U, for example, of X by open set of X. There exists a finite subset delta 0 of delta such that X minus this union belonging to I, the ideal. It means the union of this U alpha, this cover, which is alpha belonging to delta Z. It should be belong to the ideal. Theorem 10, let G star tau I be an topological group and Co is an I compact subset of G, then F is an I closed subset of G. Also, F star Co and Co star F are I closed subset of G. Theorem 11, a non-empty subgroup of H of an ideal topological group G is I open if and only if its I interior is non-empty. Theorem 12, if U belonging to IOG, then the set, it means the union of it, which goes from 1 to infinity, is an I open set in an ideal topological group. We have a lemma. If G star tau I is an ideal topological group, then the inverse of it, inverse map I, G goes to defined by Ix, which is equal to the inverse of X for all X belonging to G, is an I homomorphism. Definition 9, suppose U is an I open neighborhood of the natural element E of an ideal topological group. A subset A of G is called UI disjoint if B is not in A star U for any disjoint A and B belonging to A. Definition 10, a collection of, let's call the gamma of subset of a topological space is I discrete provided that X belonging to G has an I open neighborhood that intersects at most one member of gamma. So we have the theorem 13, let U and V be I open neighborhoods of the natural element E in an ideal topological group such that V power 4 is subset of U and the inverse of V is equal to V. It means it is symmetric. If a subset A of G is I disjoint, then the family of I open sets A star V such that A belonging to A is I discrete in G. 14. Theorem 14. So let's given an ideal topological group, then every I open subgroup of G is I closed in G. So we have this proof, which is very simple actually. So I don't go through it because of the time. Definition 11, let A be a subset of an ideal topological space, then a point X belonging to A is said to be an I-isolated point of A if there exists an I-open set containing X which does not contain any point of A different from X. So then we have the following results, which concern a subgroup of H of an ideal topological group is I discrete if and only it is an I isolated point, as an ideal isolated point. So this is our proof of the theorem, but as I said, I don't go through it because of time. Definition 12, a subset A of a group G is symmetric if this happens, and theorem 16, for any neighborhood U of identity E in an ideal topological group, there exists a symmetric I-open neighborhood V of E such that V is belonging to U. So this is an easy proof. You can see that if we take, for example, neighborhood of the identity element, and the inverse function, of course, is continuous, and then there exists an open neighborhood W of E such that W is included in U, and the inverse of W is I open neighborhood of E. And if you take the intersection of W and its inverse and call it V, which is not empty, since V is the intersection of open and I open sets, then V is I open, and clearly it is symmetric. So theorem 17, let this be an I connected ideal topological group and H a subgroup which contains any I neighborhood. Then H is equal to G. In particular, an I open subgroup of G equals G. So this is very simple proof, which concerns, of course, there are some lemmas and so on. Since H is contains an I neighborhood, the interior of H is non-empty, thus H is I open and I close, and since G is E connected, then is equal to each other. Very simple proof. Definition 13, an ideal topological group with respect to I continuity is a group G endowed with a topology such that for each A belonging to G, the translation, take for example the left and right translation with respect to A, it is, as you can see it, it goes from G to G, and it is defined the left translation with A multiply G and X multiply A for right translation are I continuous, and such that the inverse mapping is also I continuous. Another theorem, we have a ideal topological group with respect to I continuity, I component of ICE of identity E be open. Then we can see we have two statements for all X belonging to ICE. We can see that inverse, the left translation with respect to X minus 1 and the right translation with respect to X minus 1 is also open. Then ICE is subgroup. If all translations are also open, then ICE is a normal subgroup. I omitted the research, the proof, because it was a difficult actually proof with lots of notations. Theorem 19, let G be a Hausdorff ideal topological group with respect to I continuity such that left translation are continuous, also I continuous respectively, and right translation are I continuous, respectively continuous, and inverse mappings is I continuous. For any subset M of G, the subgroup, which is defined by CGM, it means G belonging to the small g belonging to big G, is MG is equal to G and is I closed in G in particular, the center of G is I closed. So we come to the last theorem. Let G be an I connected ideal topological group and E its identity element. If U is any I open neighborhood of E, then G is generated by U. So these are those results which we received actually, but this is unfinished. One can follow this and do more research about connectedness and subgroup theory concerning topological groups, and C, one can deduce the well-known results. And you can see actually an open subgroup of a topological group is closed. And if you take, for example, a connected topological group, one can see that every neighborhood of the identity element is a generating system, for example. Yes, there are lots of results about the center of the group and how we can use also the quotient spaces. For example, if you have a topological group, we didn't match. We didn't go further with this because of the time schedule. But if we have a topological group and H is a closed subset of it, then one can see if both H, the closed subgroup, and the quotient of G and H are connected. If they are connected, so it should be a proof that G is also connected. So this is a very nice result one can get. Also, if we take the interior of the connected component of G containing E, if we take it, then we can see that the connected component containing E always is a closed normal subgroup of the group, the topological group G. And the one can also study the factor group and see if it is totally disconnected when we introduce ideals. So there are lots of results one can get. For example, if you have a topological group and H is a normal subgroup of this topological group, then the factor group is totally disconnected. If it is, so we can see that this connected component containing the identity, it should be a subset of this closed normal subgroup. So also concerning the solvable groups and nilpotent theory, one can use it there if one is interested in or doing research in this field. Then you can also use it in that way that if what happens if you have a topological group with some equivalent conditions, for example, which we have some results there which concerns actually solvable groups, nilpotent theory. Those who are familiar, they know that there are three conditions which are equivalent, and that's why we call this topological group for nilpotent. Okay, and then we can one can study actually the ideal theory there, introduce it there. What about the locally compact spaces? If you have a topological group, what happens there? Of course, if you have a topological group and if a subset, let's call it H, subgroup of G is locally compact, then H is a closed subset in G. So what about nowhere denseness or rate set, for example? If you have these, what happens if you have imposed, for example, in topological groups? And what about sigma compactness or contable? If you have a topological space, then how can you use it there? Okay, this is one thing which researchers, those PhD students and so on, can do research in this. Another thing is that we can take the opportunity is the multifunctions. Actually, I haven't seen any work deciding ideals or involving ideals in multifunctions. So this is very nice research area to do. Moreover, we talked about algebraic topology and so on. I think I haven't seen any notion like multifunction defined in homotopy theory. So it is very nice if somebody works in this area. Actually, to the late Naimpali, Professor Naimpali, when I was in Greek, we talked about it, but unfortunately, he got sick and we couldn't follow this work. It is a very good idea if somebody is interested to introduce multifunctions in homotopy theory, then it is a whole new area actually to work on this subject. So that's it. Thank you very much for inviting me, and thank you again, organizing committee, everybody involved to make this virtual seminar possible. Thank you very much.
Thank you, sir. Dear participants, if there are any questions, any queries?
If you have any queries, you can unmute your mic and you can speak. Sir, there is one question from the chat box.
Yes, why it is not? Because there is a question concerning why intersection is not. It is because actually it doesn't make the ideal theory consistent. That's why we don't have the intersection.
Oh, thank you, sir.
So when you make definitions, then the definitions should fit with fix some problems, and should explain the theory, should be helpful. If you define it in such a way that it makes some problems, then you throw it away. For example, you cannot divide with 0, So these sort of things, you cannot, or in combinatory, for example, if you have factorial, for example, notations, you cannot, 0 factorial is equal to 1, not equal to 0. This is the way we do it, in mathematics.
Thank you, sir, for the imprints made by you, and hope that the participants will seek the knowledge and imbibe from your presentation.
Thank
Your
you very much.
support
Thank you.
and guidance
Thank
will
you.
enrich the quality of research. Thank you, sir. Hope to meet
Thank
you in
you.
the future after this pandemic by organizing such seminars and workshops. So thank you so much, sir, for accepting our invitation and for being with us, spending your valuable time with us. Thank you so much.
Thank you. It was an honor. Thank you very much.
Excuse me.
Thank you.
Myself, Dr. Devi, former principal and HOD of mathematics. Now, from this explanation and everything, now our mathematics students must have full knowledge of topology and also algebra. If you are very strong in those two fields, when you are studying your BSc or MSc course, as per the professor's speech, we are very easily find research topics. So professor took that ideal topological space and also ideal topological group. So he explained the regular, normal spaces, etc. And also in algebra, this homomorphism, everything. So we should, everybody who are joined here should know that it is very, very easy to do research in mathematics if you are strong in algebra and topology. Thank you, Professor, for your very basic, and also the students who are studying BSc and also MSc, they can easily understand how to do research in this topology when one understand the basic things in topology and algebra. So thank you, Professor, for your guidance and also the help you have already rendered for our staff members when they were students under my guidance. Thank you so much for your guidance, sir. Thank you, Professor.
Thank you.
Excuse me.
Sir?
This Dr. Hakim speaking.
Yes, sir.
Yes,
Hakim,
sir.
sir.
Yes, sir.
How are you, sir? How are you? And it is really great lecture from Professor Said Jafari.
Thank you.
He is open new windows for researchers to us. And it is really great lecture. I am happy to be with you. And inshallah, tomorrow will be my lecture, inshallah.
Thank you.
I'm happy with you to be
Thank you
with
very
you.
much. Thank you very much, Hakim.
Sir, pleasure to have you, sir. Hakim, sir. We'll be having a session tomorrow.
Inshallah.
Yeah,
Thank you,
sir.
sir.
Thank you. Thank you.
Ma'am, thank you so much. Always you are like mother for us, and we'll incorporate the suggestions what you gave for us, and always we'll follow you. Thank you, Devi ma'am. Thank you so much.
Welcome, welcome.
We have another eminent person as a resource person for today's session. I request Dr. M. Venkatachalam, Assistant Professor of Mathematics, to introduce the chief guest. Sir, Venkatachalam, sir. Dear participants, there is a technical issue. It will be rectified.
Dr. M. Parimala, currently working as an assistant professor of mathematics at Bannari Amman Institute of Technology, Erode, Tamil Nadu, India. She has completed her PhD in the field of topology under the guidance of Dr. R. Devi Madam, our former principal and associate professor and head of mathematics, Tamil Nadu Arts and Science College, Coimbatore. Dr. M. Parimala has published more than 84 research papers in the various international journals and presented 14 papers in the conferences. She has 14 years of experience in teaching and 9 years of experience in research. Also, she has delivered 7 invited talks in various colleges. She has organized 4 conferences and 1 workshop in mathematics. It is my honor to state that she has totally 338 citations. In particular, there are 168 citations in this current year 2020 alone. There are 2 scholars awarded PhD under the guidance of Dr. M. Parimala, and currently 4 research scholars are pursuing their PhD under the guidance of Dr. M. Parimala. I wish to state that in one of the current field of research is Neutrophilic Topology. Dr. M. Parimala has published a good number of papers in the field of Neutrophilic Topology. Also, she has published some papers with the collaboration with the leading professors in neutroscopy in the country like Morocco, USA, etc. Now, I hand over the session to Dr. M. Parimala to deliver a talk on neutroscopic topology and its applications. Thank you.
Thank you, Professor Venkatachalam. Good evening, one and all present here. It gives me immense pleasure to be a part of this international seminar on topology and its applications. I thank the management, Dr. Gokulavani ma'am, Head Department of Mathematics, and Dr. Vigneshwaran and the organizing committee members of Tamil Nadu Arts and Science College for giving me this wonderful opportunity to deliver the invited talk in this august occasion. I am really happy that I am going to give a invited talk for the college which I have studied, and I am an alumni of this college. I am grateful and privileged to share this platform with the great legends of topology like Professor Said Jafari, Professor Benchali, and Professor Hakim Otam. I thank Dr. Professor R. Devi ma'am, my guide, and more than that, she is next to my mom. All that I achieved in the field of research is all because of you, ma'am. From my bottom of my heart, I thank you so much, ma'am. I am working with Professor Said Jafari from 2009 onwards. From the beginning of my research, I'm working with him. Now I got an opportunity to share this platform with him too. It's really great, and I got an opportunity to meet him in virtually too. I'm really happy for that. And let me go to my talk. I'll present my screen. I think it's visible, right?
Yes, ma'am, it's visible.
Yeah, thank you. Yeah, neutrosophic topology and its application is my topic today. Actually, before I would like to go to neutrosophic topology, let me just give a glimpse about what is neutrosophic set theory, then what is topology, then I'll just go with the collaboration of what is neutrosophic topology then. So that's my idea about today's talk. Yeah. Actually, before going into neutrosophic set theory, one must know few things about what is a fuzzy set theory, intersynergistic fuzzy set, and neutrosophic set. For that, actually, being a topologist, we'll be very clear about what is a crisp set. Okay, crisp set is nothing but we'll be talking about the data which is exactly in the set. Okay, so that gives a clear idea. Like once if you are asked to tell an answer, like yes or no type of questions, it is not always true in all the cases. Like if somebody asks you, "Are you hungry?" Right? You have to say only two answers. One is yes or no. This is an example for crisp set. Okay, either we have to go inside that yes concept or no concept. But sometimes that is not applicable for real time cases because I might be hungry slightly, not starving, but I may be hungry lightly. So how to express that with keeping crisp set? That's where the beginning or origin of fuzzy set theory. Fuzzy set theory was introduced by Professor Zade. Many of you know that, but even then, I'd like to tell few ideas about what are the origin or basic concepts about all these things. Then we'll go with neutroscopic set. Because fuzzy set theory was introduced by Professor Zari in 1960s. By that time, there was a great debate between what is a fuzzy set theory, why it came, once if the probability set is already existing. Okay, researchers are very much comfortable with probability set, and they just questioned like why you have to go with fuzzy set instead of probability. Yeah, there is a difference between fuzzy set theory and probability theory, because in probability we'll be just dealing with a well-defined objects, right? Well-defined collection of objects. You know all the set of all elements which is present in the set, right? But in fuzzy set, even if it is a vague data, we can use fuzzy set theory. Yeah, that is the basic idea about or the difference about fuzzy set theory and probabilistic theory, right? Right. Why this fuzzy set? Where it is applied? Once if you ask the question, whenever you just go with a mathematician, we'll be having a question like where you'll be applying. What is the application for that? This question will be there in every presentation. Like whenever I just go for a presentation in a conference, I used to give topological results and everything. Yeah, but finally they'll be asking one question that we couldn't, I couldn't answer is where it is applied, right? So I just searched like where and all it is applied. Like from basics I started. So fuzzy set theory has got many applications. Like in air conditioner it is applied, right? How it is applied? If you ask the question, I'll say that air conditioner, if you are just switching on it, it will just make the room cool, right? But after a few minutes, there may be fluctuation. Some very number of persons comes inside, the temperature will get raised. So by that time, it has to analyze the temperature fluctuation, and it should automatically convert its temperature to cool mode, right? So this is done by using fuzzy concept, right? Similarly, in like washing machine, TVs, what about it, smart TVs, everywhere it is applied. Like if the power is high, okay, if the light is high, it should change its frequency of radiation. That can be done by using fuzzy set theory. These things are done using fuzzy set. So after 1960s, there got some generalization needed, as fuzzy set talks about only the membership values, how far it is belonging to the set. But inclusionistic fuzzy set has also included another term called non-membership. How far that is not in the set, that can also be dealt. That was introduced by Atanasoff in 1975. In 1975, Atanasoff introduced the concept of inclusionistic fuzzy set. In this, he dealt with two things. One concept is membership value. The other concept is non-membership value. How far it belongs to the set and how far it is not belonging to the set. Both will be involved. That gives a clear idea about membership as well as non-membership. I'll give an example for that. If you are served with a hot tea, if the tea is hot, how far you can tell that it is not exactly too hot and it is not exactly too cold. So you have to generalize it, how far it is cold and how far it may be 70% cold, 70% hot and 30% cold. That can be analyzed by using inclusionistic fuzzy set. There too, something is missing. That is done or that is filled by Neutrophilic set. Yeah. So that Neutrophilic set theory is the generalization of fuzzy set, inclusionistic fuzzy set, and very many concepts, right? Paracompact set, likewise. So Neutrophilic set deals with three things. One is membership value, the other one is non-membership value, and the third one is indeterministic value. I'd like to introduce few legends behind the Neutrophilic set theory, like Florentin Smarandi. So this professor is the founder and inventor of this Neutrophilic set theory. He invented this set in the year 1995. He also owns a journal called Neutrophilic Sets and Systems. So this is what this journal run by Professor Smarandi. And he is just supporting researchers from different fields. So those who are doing Neutrophilic set field, right? And Professor Salama, this professor is from Egypt. He has introduced the concept of crisp neutrophilic topological spaces. He has also done many research papers in neutrophilic set based problems. And Professor Said Rumi, he has done research in the field of neutrophilic graph theory. He is also running a journal called International Journal of Neutrophilic Science. So these legends, along with Professor Said Jafari, are doing a very good research in the field of neutrophilic sets and systems. Now, neutrophilic, I told you that it consists of three different things, and the neutrophilic technique consists of two things widely named as certainty and uncertainty. Yet certainty deals with truth and falsity, how far it is true and how far it is false. And uncertainty may be like if the data is not clear. That is like if you have some ambiguity. That is, you are not clear about the data, or there may be some ignorance. You don't know what is the output. Likewise, or contradiction to it, or neutrality. It may be, it will not be true and it will not be false. Either you can say both, right? So by that case also, we can just use the uncertainty concept. And saturation, the results are not that much clear. All these cases can be done by using neutrophilic technique. It consists of three things. One is truth, membership. The other one is falsity. The next one is uncertainty. It may be like ambiguity or ignorance, or you are not familiar with that data. Everything can be done with the help of neutrophilic. So this neutrophilic part contains all the wholesome data, even if the problem doesn't contain a clear data. Right. I told you that there are few examples, like in probability, what you will say, the probability of tossing a coin is either head or tails. We will never talk about this event. Okay, the probability of getting neither a head nor a tail is not at all possible. We used to say this is an impossible event as far as probabilistic is concerned. But this may also happen in real life, right? If a coin is tossed inside a sand or inside a uneven surface, what will happen? A coin may like this. So this is the case where a probability concept fails. So either a head may be there, either a tail may be there, or even this case is also possible, right? So this is where the uncertainty happens. And what about here? A dice facing either 6 or 4 or 3, we don't know, right? It shows all the 3 faces. In this case also, we just lack information correctly. So this type of information can be solved by using Neutrophilic sets, right? Once a coffee is served, we'll say that 70% it is hot and 30% or 20% it is cold outside. What about the cup surface? Cup surface might be having a temperature in between. It's not even that cold like coffee, not even that hot as the surrounding. Likewise, it may be, right? So these are the real life examples where Neutrophilic set theory should be applied. Yeah. Now, Neutrophilic logic, what it deals. As I told you that the framework is the unification of many existing logics, such as fuzzy logic, inclusionistic logic, and main idea of Neutrophilic logic is to characterize each logical statement in a 3-dimensional space. The 3-dimension space consists of 3 things. One is the truth value, and the falsehood value, and the indeterminacy value. This indeterminacy value is what I told you. The data may not be clear, or the data may be not that much adequate, or it is not appropriate. All those cases comes under indeterminacy part. So what about these values, where it lies? So it lies between 0, minus and 1 plus, right? So within the interval of 0 and 1, it will lie. So this is the set or 3-dimensional view of a Neutrophilic set, geometrical figure. That is, it consists of truth membership. That is, T of x is nothing but the truth membership. I of x is nothing but the indeterminacy membership. And this is nothing but the falsehood membership. So the value can be identified by using this figure. This can show you a clear idea about the 3-dimensional view of a Neutrophilic set theory. Here, this whole box, if a point lies here, you can able to identify the value for truth and indeterminacy and falsity easily. Now, if the data are lying in the middle of this 3-dimensional area, there you can use the interval value Neutrophilic sets, right? I'm not going to deep into that first. Let me just give what is the idea about Neutrophilic set alone. Now, the Neutrophilic set, mathematically it is defined as, let capital X be a non-empty set, then A equal to set of all X. So this is nothing but the element X, which belongs to capital X, such that it consists of 3 things. One is membership of the X, I of X is nothing but indeterminacy of X, and N of X is nothing but non-membership of X. Yeah. So this is the set called as Neutrophilic set. And the condition, only condition is that it should lie, if you add all these components, it should lie between 0 and 3. Yeah, as I told you, each element lies between 0 and 1. So if you add all these things, it should lie between 0 and 3. Yeah. So basic operations of this Neutrophilic logic are nothing but a set A is a subset of B only if the membership of A is less than membership of B, indeterminacy of A is greater than indeterminacy of B, and non-membership of A is greater than non-membership of B. So if this is satisfied for all the elements belonging to X, then you can say that A is a subset of B, right? And if the set is said to be equal, only if A is a subset of B and B is a subset of E. This condition is satisfied means that you can say that both the sets are equal. And intersection is nothing but minimum of membership of A and B and maximum of indeterminacy of A and B and maximum of non-membership of A and B. This will give the intersection operation. So this will give a value that is A and B. Okay, and A union B, that is A or B, can be identified by using maximum of membership of A and B, minimum of intersection of A and B, and minimum of non-membership of A and B. Usually, Laurentins Marande used to say that the truth membership has a separate value and indeterminacy should be joined with the non-membership value. That will give a clear idea about the problem. Okay, that's why we are using maximum for indeterminacy and non-membership and minimum for membership value. We'll just group it like membership is different and non-membership and indeterminacy together. Yeah. Now, an example I'd like to tell you that once if you are given a mobile phone, so suppose we are getting 100 calls, yeah, per day. So if you are getting 100 calls per day for that particular phone means there may be 60 calls were received truly. So 100 calls, out of that 100 calls, we will be receiving 60 calls that you have answered. You have attended it and you have answered it. Out of which 15 maybe numbers are saved that you have saved in your mobile and 10 numbers are unsaved numbers in the mobile. So anyhow, you have attended 60 calls. All those 60 calls can be considered as the truth membership. So 60 calls will be truly truth memberships that can be written as 60 by 100, that is 6. So 0.6 is the membership value. And 30 calls were not received by a mobile holder. So you have not received the call. So that means what it is, 20 calls which are saved in your mobile contact or not, whatever it may be, but you have not attended. Either you are not willing to attend the call or you are not you just left the phone at the home or you are in the meeting, whatever it may be, right? You have not attended those calls. So those calls are nothing but indeterminacy calls. Why I call that as indeterminacy calls means you might have got, if you are there, you might have attended the call. Okay, that's why we are just putting this as indeterminacy membership. But anyhow, you have not attended the call. But if you were there at the spot, you might have attended the call. That is ambiguous. So that's why we have put that 30 calls as indeterminacy memberships. And remaining 10 calls you might have rejected. You might have cutted the call. Okay, either you are not interested to talk to him or it is not a saved number, whatever it may be. But you have cut the call by you. So 10 rejected calls will be the false values, that is 0.1 membership value. So I think this example gives you a clear idea, right? The calls that you have attended is nothing but the truth membership value. The calls you have cutted is nothing but the false value. But the 30% of the call that you have not attended, you have left the phone somewhere or it is in silent mode, or if you are in some meeting, whatever it may be, but you have not attended the call, that comes under indeterminacy call. So why this Neutrophilic set? Where and all it is applied means it is applied in many areas like psychology, sociology, civil engineering, information technology, linguistics, probability and statistics, calculus, algebra, topology, graph theory, decision making, and many more. Right? I could find only these things, so I have just listed few of the things which I have just gone through. Yeah. Now I'd like to tell about my own topology. Right? Topology is the branch of pure mathematics that deals only with the properties of figures X that holds for every figure into which X can be transformed with one-to-one transformation with one-to-one correspondence that is continuous in both directions. Right? This is the mathematical definition. Topology is concerned with the properties of geometric objects that are preserved under continuous deformation, such as stretching, twisting, crumbling, bending, and but it is not allowed to tear and glue. That's it. So, like Vasiki ma'am told, this topology has got several many applications in engineering, medical, biology, and many things, right? I don't know this for past 3 years. I were blank about where and all this topology is applied, but now I could say that this topological concept is applied in many things. Like I'll just tell you one example that I have attended a seminar in mechanical engineering. There they have just applied a topological concept and they have done tremendous research in topology, right? So what they did is for an elbow, they are just going to frame a design so that once a person gets fractured and if he need to be replaced with that material, that should not tear and it should be flexible, and according to the movement of the hand it should move, right? So there they have just framed a tool that will work instead of this elbow, right? So that they have applied the topological concept fully, right? So topology has got a tremendous application. Yeah. So topology is nothing but the surface study, and it is a way in which the parts of something are arranged, are related, and how they are related, right? And who cares about topology? That I have got a video. If time permits, I'll just show you, or else I'll just share this link with you. You can just see the video. Yeah. Now, if we go to the Neutrophilic topology, a Neutrophilic topology, in short, NT, is a non-empty set X is a family of tau, collection of tau. Like what we'll do, we'll just take a collection of sets, subsets, such that it should start by some axioms, right? Here, 1n. This is similar to our crisp topology, like whole set and null set belongs to topology tau. Like 1n and 0n belongs to tau, and finite intersection of two neutrophilic sets belongs to tau for any A1 and A2 belongs to tau. An arbitrary union of any sets in tau can be taken and it should be in tau. This is the basic definition of a neutrophilic topology. This is an example. Let me consider capital X is a singleton element X and capital A equal to set of all 0.5, 0.5 and 0.4. Here B is nothing but 0.4, 0.6, 0.8 and B is 0.5, 0.5, 0.4. I should take an element of membership, indeterminacy and non-membership. And C is nothing but 0.4, 0.6 and 0.8. So these are the four sets I have taken in terms of this X element. Okay, these are the membership, non-membership and indeterminacy values of this X. Then the family of X comma tau can be written as set of all 1n, 0n, A, B, C and D all together forms a neutrophilic topology on X. Each set in tau is open and its complement is closed as usual as what we do in this crisp topology. The same thing is done in neutrophilic topology. Here neighborhood, the neighborhood concept of a neutrophilic set A is the neighborhood of neutrophilic set B if there exists an open set C such that B is contained in C, which is contained in A. So this is the definition of a neutrophilic neighborhood and interior enclosure. How to find the interior enclosure is nothing but enclosure of S is equal to minimum of set of all neutrophilic closed sets that are contained in F and maximum of set of all F such that F is contained in S is nothing but neutrophilic closure of S and neutrophilic interior of S. Let A be a neutrophilic set in a topological space X comma tau, then A is equal to interior of A, then you can say that set A is open. A neutrophilic set is said to be neutrophilic closed if and only if A is equal to neutrophilic closure of A. Now here if let us consider A and B are two neutrophilic sets, then the following properties holds. That is neutrophilic interior of S will be a subset of S and S is a subset of neutrophilic closure of S. S is a subset of P, then N interior of S is also a subset of N interior of P. S is a subset of P implies n closure of S is contained in n closure of T. And n interior of S can be written as n interior of S intersection n interior of T. N closure of S union P can be written as n closure of S or n closure of T. And n interior of 1 is nothing but 1. And n closure, Neutrophilic closure of 0 or empty set is nothing but empty set. These are the basic properties that belongs to two sets contained in a Neutrophilic topology. Now, the basic weaker open sets are nothing but semi-open, pre-open, alpha, and beta open. These sets we might have studied in general topology. That same thing we are just going to deal with Neutrophilic set theory 2. There is Neutrophilic semi-open is nothing but A contained in n closure of n interior of A, and Neutrophilic pre-open if A is contained in n interior of n closure of A. Alpha open means A is contained in n interior of n closure of n interior of A, and beta open if A is contained in n closure of n interior of n closure of A. So all these open sets and its complements are nothing but closed sets. N semi-closed, N alpha closed, N pre-closed, and N R closed. All these things we can just go. These are the basic definitions. And about right, Neutrophilic pre-open and semi-open and alpha open is also given. Then let me just go with. I have just introduced the alpha set closed set. That the definitions involved in this alpha set closed sets are nothing but Neutrophilic semi-generalized closed. That means that semi-closure of A is contained in U whenever A is contained in U and U is semi-open. If this condition is satisfied, then you can say that set is nothing but Neutrophilic semi-generalized. Similarly, psi closed set and Neutrophilic alpha psi closed set is nothing but whenever A is a subset of U and U is n alpha open, then psi closure of A is a subset of U. So if this condition is satisfied, then one can say that the set capital A is nothing but Neutrophilic alpha psi closed set. And Neutrophilic alpha psi interior is nothing but set of all Neutrophilic alpha psi open sets in X only if G is contained in A. And Neutrophilic alpha psi closed is nothing but intersection of set of all Neutrophilic alpha psi closed set such that G is contained in A. Then Q coincident, two sets A and B are said to be Q coincident if and only if there exists an element Y such that A of Y plus B of Y should be greater than 1. If the addition of these two sets elements, then you can say that it is greater than 1. Yeah. Then two Neutrophilic sets A and B, negation of A, Q, B if and only if A is contained in B complement. Then the Neutrophilic topological space is Neutrophilic alpha set connected between Neutrophilic set A and B. Then the Neutrophilic connection between A and B is there. So then there will be a Neutrophilic connectedness. If alpha set connectedness is there, then you can say that it is connected. So the proof is given like if two sets are Neutrophilic alpha psi connected, then you can say that it is already closed and open set in F such that A is contained in F and negation of F cube B both will get satisfied. Then F is Neutrophilic alpha psi closed and F is Neutrophilic alpha psi open. Therefore, you can say that it is not a Neutrophilic alpha psi connected between A and B. Therefore, we have just taken contradiction. So now we have just proved that it is a contradiction to our hypothesis. Similarly, I have just proved a few many theorems related to Neutrophilic topological space. That is Neutrophilic alpha psi connected between Neutrophilic sets A and B if and only if there is no Neutrophilic alpha psi closed and Neutrophilic alpha psi open set in A. Set F in X such that A is contained in F and which is contained in B complement. There is an interrelation between these two sets that has been proved by necessity and sufficiency condition. So this is another theorem. I think let me go with the application part right now. because I have just done few theorems. So here, like Y be a neutrophobic closed subset of a neutrophobic topological space X comma tau, and A and B be neutrophobic subsets of Y. Then if X comma tau is neutrophobic alpha say connected between A and B, then so is the subset also, right? So A and B are two subsets of Y, and if X comma tau is alpha say connected, then you can say that Y comma tau Y is also alpha say connected. That is what we have proved in this result. Now let me go with the application of neutrophobic problem, right? From the problem to neutrophobic decision. How a problem will be provided, and from there how to go with the decision making. That's what I have done as an application part for this neutrophobic topological space. The mathematics is used to transform the problem into data, then the process it, then we have to process it, then we have to get the information and organize the information, then we have to convert the problem into the solution by using our wisdom and knowledge of decision making, right? So these are the steps involved in problem to decision making, right? If you are just given with a raw problem, there you have to collect the data of neutrophobic. By using the neutrophication, you can convert the real-time problem to a neutrophobic data. From there, you can just collect what are the information that are available by using neutrophobic information. Then we'll use the knowledge and we'll use the neutrophobic decision. So neutrophobic decision can be done in several many ways, like Topsis algorithm, ASP algorithm. Likewise, there are several many algorithms available. By using those algorithms, we can use the neutrophobic decision. Then from there, using our wisdom, we can just get the optimum solution. So now we are just going to see what is the neutrophobic topology and how it is applied in data analysis. So decision making problem with a single value neutrophobic information, the following necessary steps are proposed. Here we just take two types of things. One is attributes and alternatives, and attributes with decisions. So keeping all these things, we are just going to make a decision, right? Here C1, C2, C3 are nothing but the alternatives, right? And A1, A2, A3s are nothing but the attributes. Like I can give you an example, like if four types of patients are coming to a hospital, to a doctor, particular doctor, and they will tell the suggestions, like these are my symptoms, and accordingly I get this type of disease. So the doctor has to come to a conclusion with the set of all symptoms they tell related to the disease, and according to the disease they have to give the medicine. So this is the procedure. As far as we go to the doctor and we'll just say all the symptoms to him clearly. So according to our systems, he will just come to a conclusion that this patient is affected with this disease. So coming to that conclusion, he will decide what type of medicine can be given to that particular patient. So that is what the alternatives and attributes are about, right? So this is a simple example I have told you. I'll just explain you with another example also. So C1, C2, C3 are nothing but the alternatives. A1, A2 and A3 etc. are nothing but the attributes. Here these attributes again are related with another type of attributes like D1, D2, D3 etc. So these are the alternatives and attributes table. So once the data is given like this, what we have to do is we have to just decide the problem field. So consider the multiple attribute decision problem with m number of attributes, n number of alternatives, and p number of attributes. So these are the set of data we get it, right? From that values, you have to form the neutrophobic topologies for CJs and DKs. So these alternatives and the attributes, we are just going to frame the topologies like PIs and KJs, right? So here we have identified the set of all values in the table. So what I have done in the previous, these values are taken and their union and the intersection. So all the topological values comes in. That is, we'll get the null set, whole set, and the arbitrary union and finite intersection. Everything should be in tau I. Similarly, we have to do for KJs. Now we'll get the set of all topological values. Then from that we have to convert the neutrosophic values into a normal value. That is, we have to convert the deneutrosification can be done by using a score function. That is done here. Find the single value neutrosophic score function like NSF equal to sum of all I lies between 1 to m, 2 plus ms minus I minus n. This gives the score value for all those topologies. For individual, each and every topology, will find a score function. Then from that score function, we will find NSF CJ and NSF DK. Right? So sum of all the score values gives you the score value or the deneutrosophicated values. Finally, we have to arrange the decisions in run-up order, C1, C2, C3 likewise, and D1, D2 likewise. Here we have to choose C1 to DP and C2 to DT minus 1, etc. Likewise, we will just calculate and find out the values. So this is the algorithm for finding the decision. Here we will just go to the application part of the proposed algorithm, right? So application and allocation of work in computer fields, right? So here let us take some attributes and alternatives, right? The process of classifying different set of persons with skills for single work is very difficult, right? Because each and every person has got their own specific talents. So keeping those specific talents, we have to identify this person is suitable for this job, right? So here in computer field, some people will be well versed in software, and some will be well versed in programming, some will be well versed in software. Hardware, software, and programming skills. Many different skills are there. I'll just take one or two things. So we have to pick a person according to the job nature, right? So that situation is what we are going to take here, right? So analysis of persons involves more indeterminacy, because we might be thinking that he will be having that much of skill, but he will not be that much appropriate with that skill. That can be identified by using this neutrosophic values. So the proposed topological measure among the programmers versus skill, and skill versus work allotment. So that is what I told you. The set of all programmers and their skills is one attribute, and skills and versus work. What type of work should be allotted, that can be done here. So step one is like we have to choose the problem field. Let us consider three set of programmers: person 1, person 2, and person 3, and three different type of jobs like job 1, 2, and 3, and the set of all attributes or skills that they are processing are nothing but C as Windows Web Satcom. So these are the different type of works done by them and their skills. Okay, how far they are skilled in these things. So that attribute is given. So programmer 1 in C has he is well versed up to 80%. He is well versed, and 0.2% he doesn't know, but 0.2% he might be in dilemma, right? So likewise, we have just filled up all the data, and here it is like skills versus projects. So this much of skills is necessary for this project, job 1, right? Windows, it needs just 40% of truth membership for job 1, right? So likewise, the data like skills versus projects is also given. So keeping this, we are just framing the topologies. So topology 1 and 2 and 3 from table 1, from this table 1. That is programmer versus skill that we have done. And this is from table 2. That is the skill versus jobs. From this, we will just calculate the neutrosophic score functions. So from this topology, each and every topology, I calculated the topological attributes like C1. This much of score value I got, C2 it got 0.50553 and C3. And according to the table 2 and topologies, we get this values. So from these, we'll just arrange it in the run-up order, and we'll come to a conclusion like program on 1 will be suitable for job 1, program 2 is suitable for job 3, and programmer 3 will be suitable for job 2. So this is how we can come to a conclusion. Here I have just taken a decision making problem as an application for Neutrophilic topology. So as a conclusion, I would like to tell that Neutrophilic topological space is one of the research area of generalized fuzzy topological space to deal the concept of vagueness, right? So many researchers can do work, or many work is available in Neutrophilic topological space. So anybody interested can come to this field of work. So this work was introduced Neutrophilic topological space and its real-time application. So in this talk, I have just gave a glimpse about Neutrophilic logic and topology, and also its real-time application. But it has got lot of applications. So many can do research in this field. So this theory can be developed and implemented to other research areas of general topology, such as rough topology, nanotopology, supra, digital. Everything can be done in terms of Neutrophilic set theory. So this is the home page. You can just go to the home page of Florentine Smarandi. This page, I think I can show you. So this is Professor Florentine. This is his URL page. Here you can just see a number of research done from 1995 to till date. He has updated everything. So you can learn many things here. Right? I started my research in terms of Neutrophilic topology by the guidance of Professor Jafari in the year 2016 actually. So from then I am introduced to Neutrophilic set theory, right? So if you are interested, there is a big opening for you all to do research in Neutrophilic set theory. And what else to say? Yeah. And also NSS Neutrophilic Sets and System Journal is also available. You can just go to it. You can type it, it will come. Okay. So this is my mail ID. If any queries or anything, if you would like to tell, you can just feel free to just contact me. And thank you. Thank you all for your rapt attention. Thank you so much.
Thank you, ma'am. Dear participants, if you have any queries, you can unmute your mic and you can ask now.
Yes, I got few.
Fuzzy Neutrophilic set and Neutrophilic sets are different, ma'am.
Yeah, actually, crisp Neutrophilic set theory is also available. Fuzzy Neutrophilic set theory is also available. You can just, yeah, both are different actually. Crisp and fuzzy Neutrophilia are different. And yeah. So John sir, you have got a question like 0 less than or equal to, yeah. This, yeah, I can explain you this. Sometimes what will happen now, it will not lie between 0 and 3. Why it does not lies between 0 and 3? Because I can give you an example like every country will be having a few spies, right? If you just consider, can you mute yourself, Professor, please? Yeah.
Okay.
Noise from your side. Yeah. Some, yeah, if you consider, what say, yeah, spy agent, what will happen? He will just give some data to the neighboring country, right? If a Pakistani is here in some higher official, he will just spy our country and he will give it to the opponent country, right? By that time, he will be a membership of this committee, but he will be working for our against our country, right? So by that case, he will be a negative member.
Okay, ma'am.
So he will just give negative values to, so that will affect our security of our country. So in that case, it may be less than 0.
Okay, ma'am. Okay, ma'am. I understand.
Yeah, similarly, it may be more than 3 2.
Okay.
Sometimes, rare cases, it may happen. That's why it is given 0, minus, and 3 plus.
Okay, ma'am. Thank you,
But
ma'am.
maximum in research, we will be considering 0 to 3.
Okay, ma'am. Thanks a lot.
I
Okay.
think I have answered your question. Thank you.
Okay, ma'am. Thank you.
Yeah, thank you, Professor Jafari, sir. It's a great pleasure for you to share this platform. I'm just, what to say, I'm just impressed. Thank you so much, Professor Jafari.
Thank you very much. Thank you very much, Paniwala. It was a very nice talk. Really.
Thank you so much. It's really great honor for me.
Thank you. Thank you.
I request all the participants to fill the feedback which is given in a chat box. I repeat, I request all the participants to fill the feedback which is given in the chat box.
Thank you, madam.
Yeah, thank you, ma'am.
Thank you, ma'am, for the wonderful presentation and sharing your knowledge with us. Hope your suggestions will help the budding researchers to pursue their research and shine in their work. And also wish always be connected with us and help our research students also. Thank you so much, Parula, ma'am. Thank you so much for having our alumni with us today.
Yeah.
Thank you.
My mail ID I have given you. Anybody interested in the research field can just approach me. I'll help you at any step, right? Thank you so much.
Thank you. Thank you, ma'am. Thank you.
So it's a gentle reminder for all the participants that tomorrow we have a session with two eminent speakers, Dr. Hakim A. Othman from Saudi Arabia and SS Benjali from Karnataka at 3 p.m. through the Google Meet with the same link. YouTube Live will have a different link which is posted in your email later. So thank you so much. We would like to thank you all again for your gracious presence. Thank you. Thank you, one and all.